When it comes to the history of science, there is nobody who is more popular in many ways than this man, Albert Einstein. But why is he such a big deal? Why is Einstein such a big deal? Because what he did was he took down somebody else from, someone else's paradigm. He took down that paradigm. So let's do a comparison between Einstein and Newton. This is going to take more than one video, but what I want to do is first of all, let's turn to Einstein's theory of relativity. So basically, this is from the OpenStax. We're going to go down the list here. So from the OpenStax textbook, this is the University Physics Volume 1. My students are going to be studying Einstein's theory of general relativity. There's a channel on YouTube that does a great job of talking about some of the intricacies about Albert Einstein. Physics for Students is the name. I do want to give a quick disclaimer when it comes to this topic in physics or just anything physics related. Just because I'm a physicist does not mean that I agree with everything that the establishment in physics might say. So I am one of those physicists that is like Isaac Newton and James Clerk Maxwell, who believes that God made the world, so now we can study the world that God has made. So because, it says in the Bible, in the beginning, God created the heavens and the earth. Because God made the world, it makes sense that the world obeys laws, right? So that's the natural theology, the framework that I'm coming from. I believe the universe is designed. I believe that God made the world, and I want to study the world God has made to the fullest extent. I want to be one of the people who inspires the next generation of Isaac Newtons, James Clerk Maxwell's, the best mathematicians and the best physicists. So let's now look at Einstein's theory of general relativity. So the learning objectives for this chapter, we're going to describe how the theory of general relativity approaches gravitation. We're going to explain the principle of equivalence. We're going to look at the Schwarzschild radius of an object, calculating that, and then we're going to summarize the evidence that is given in physics for black holes. Okay, so let's look at the first part. So Newton's law of universal gravitation accurately predicts much of what we see within our solar system. Indeed, only Newton's laws have been used to accurately send things into space, right? So Newton's laws has been used to send things into space on every space vehicle. The paths of Earth crossing asteroids and most other celestial objects can be accurately determined solely with Newton's laws. Kepler is an influential figure with Kepler's elliptical laws, and he gave us the understanding of the fact that, see, the sun is at the center of our solar system, and the earth revolves around the sun. It's not the other way around, right? The sun doesn't revolve around the earth. That's one of the things that Copernicus established with his work, which gave rise to a lot of what we talk about in the scientific revolution. So in the scientific revolution, which we can say from about 1500 to 1700, right? This is discussed in my book, STEM Excellence. From the scientific revolution to the AI revolution. So we're going to be examining the scientific revolution, what caused the scientific revolution, and what lessons can we learn from it as we look at the era that we live in today. And so Newton's laws were very good and are very good at a lot of things. Nevertheless, many phenomena have shown a discrepancy from what Newton's laws predict, including the orbit of Mercury and the effect that gravity has on light. In this section, we're going to examine a way of envisioning gravitation. So that's the first part. A revolution in perspective is the next thing here that is discussed. 1905, June 30th, was a big deal. Albert Einstein published 4 papers that came out and just hit the world. Boom! 4 papers. Like, Einstein did not play around. Einstein showed us things about Brownian movement. Einstein did some work which, of course, would surface through those early 1900s on the photoelectric effect. Einstein was good at thinking outside the box, right? So if you want to be a phenomenal scientist, you have to be willing to think outside the box. So what is up with this revolution? Well, in 1905, Albert Einstein published his theory of special relativity. This theory is discussed in great detail in a different section of the book. The cool thing about the OpenStax books is that you can actually go to, like, let's say it says relativity here, and you can click that, and it will take you to that specific section. That's kind of cool, right? So it would do the same thing if you had if you have a textbook, you won't be able to do it as easy, right? But now with the website, you can click on it. It'll take you to a section that talks specifically on relativity. There are 3 books in the university physics series. This is the 3rd book in that series, right? So notice that it's going to talk about the invariance of physical laws, relativity of simultaneity, the Lorentz transformation, and so on and so forth. And the cool thing with OpenStax is you can download all these books, right? Physics and philosophy are pretty much like relatives, I say, because some of these topics are going to get you thinking, what is going on? This is a little intense. So why don't we go back to Einstein's work in this chapter from volume 1, and we could do a deeper dive to volume 3 later on. So I'm going to go back, right? It's nice that you can quickly reference that and go back to where you are. This is a revolution in perspective. Albert Einstein published his theory of special relativity. So we say only a few words here about it in this particular section. In this theory, no motion can exceed the speed of light. It is the speed limit of the universe. Oh, now we get into some philosophy, but let's not go there. There's a lot of debate that can happen there. This simple fact has been verified in countless experiments. However, it has incredible consequences. Space and time are no longer absolute. Two people moving relative to one another do not agree on the length of objects or the passage of time. Almost all of the mechanics you learned in Newton's era in the previous chapters, while remarkably accurate, even for speeds of many thousands of miles per second, begin to fail when approaching the speed of light. When you approach the speed of light, we get into a different arena. This speed limit on the universe was also a challenge to the inherent assumption in Newton's law of gravitation that gravity is an action at a distance force. That is, without physical contact, any change in the position of one mass is instantly communicated to all other masses. This assumption does not come from any first principle, as Newton's theory simply does not address the question. The same was believed of electromagnetic forces as well. It is fair to say that most scientists were not completely comfortable with the action at a distance concept. A second assumption also appears in Newton's law of gravitation, which you can find equation 13.1. The masses are assumed to be exactly the same as those used in Newton's second law. We made that assumption in many of the derivations in this chapter. Again, there's no underlying principle that this must be, but experimental results are consistent with this assumption. In Einstein's subsequent theory of general relativity, which came out in 1916, and this is cool with World War One. Well, World War One is not cool, but what I mean is with World War One happening, as you look at the history of history, quote unquote, you can also see that some of Einstein's work was confirmed during World War One, and there's a very interesting story about that, which you can find on YouTube, or we can talk about it later on. Leave a comment if you want me to tell a whole story about that later. Both of these issues were addressed, right? His theory was a theory of space-time geometry and how mass and acceleration distort and interact with that space-time. It was not a theory of gravitational forces. The mathematics of the general theory is beyond the scope of this text, but we can look at some underlying principles and their consequences. The mathematics for general theory of relativity are some of the things that we cover in our Counter to Calculus series in these workbooks behind me. We want everybody to be able to understand the universe that they live in. So let us land this plane. We are going to continue the series comparing Newton and Einstein's work. I want to talk about why Einstein is such an influential figure in the history of science. So follow this channel for more. This is the beginning of our discussion on Einstein's theory of general relativity. Have a blessed day. Subscribe for more.